In mathematical logic, category theory, and computer science, Kappa calculus is a formal system for defining first-order functions. Unlike lambda calculus, Kappa calculus has no higher-order functions. Its functions are not first-class objects. Kappa calculus can be regarded as a reformulation of the first-order fragment of types lambda calculus. Because its functions are not first-class objects, evaluation of Kappa calculus expressions does not require closures. Definition. The definition below has been adapted from the diagrams on pages 205 and 207 of Hasegawa. Grammar. Kappa calculus consists of types and expressions, given by the grammar below. In other words, one is a type. If an a types, then is a type. Every variable is an expression. If is a type, then is an expression. If is a type, then is an expression. If is a type and is an expression, then is an expression. If and are expressions, then is an expression. If x is a variable, is a type, and is an expression, then is an expression. The and the subscripts of it, and are sometimes omitted when they can be unambiguously determined from the context. Juxtaposition is often used as an abbreviation for a combination of and composition. Typing rules. The presentation here uses sequence, in other words, VAR. Assuming lets you conclude that id for any type, bang for any type, comp. If the target type of matches the source type of, they may be composed to form an expression with the source type of and target type of. Lift. If, then. Kappa. If we can conclude that under the assumption that, then we may conclude without that assumption that. Equalities. Kappa calculus obeys the following equalities: neutrality, if then and, associativity, if and then, terminality, if and then, lift reduction, Kappa reduction, if x is not free in H. The last two equalities are reduction rules for the calculus, rewriting from left to right. Properties. The type 1 can be regarded as the unit type. Because of this, any two functions whose argument type is the same and whose result type is 1 should be equal, since there is only a single value of type 1. Both functions must return that value for every argument. Expressions with type can be regarded as constants, or values of ground type. This is because 1 is the unit type, and so a function from this type is necessarily a constant function. Note that the Kappa rule allows abstractions only when the variable being abstracted has the type for some. This is the basic mechanism which ensures that all functions are first-order. Categorical semantics. Kappa calculus is intended to be the internal language of contextually complete categories. Examples. Expressions with multiple arguments have source types which are right-imbalanced binary trees. For example, a function f with 3 arguments of types a, b, and c and result type d will have type if we define left associative juxtaposition as an abbreviation for then, assuming that, and we can apply this function. Since the expression has source type 1, it is of ground value, and may be passed as an argument to another function. If, then, much like a curried function of type in lambda calculus, partial application is possible. However, no higher types are involved. Note that because the source type of is not 1, the following expression cannot be well typed under the assumptions mentioned so far. Because successive application is used for multiple arguments, it is not necessary to know the arity of a function in order to determine its typing. For example, if we know that then the expression is well typed as long as J has type for some in. This property is important when calculating the principal type of an expression, something which can be difficult when attempting to exclude higher-order functions from types lambda calculi by restricting the grammar of types. History. Barandiga originally introduced the term functional completeness in the context of combinatory algebra. Kappa calculus arose out of efforts by Lambert to formulate an appropriate analog of functional completeness for arbitrary categories. Hasegawa later developed Kappa calculus into a usable programming language including arithmetic over natural numbers and primitive recursion. Connections to arrows were later investigated by Power, Thielecker, and others. Variants. It is possible to explore versions of Kappa calculus with substructural types such as linear, affine, and ordered types. These extensions require eliminating or restricting the expression. In such circumstances, the type operator is not a true Cartesian product, and is generally written to make this clear.